Welcome, this is Information Service Engineering lecture number 5, Basic Machine Learning. In this section of the course we will have a look at basic machine learning algorithms, and we will start with linear regression. First of all, there are lots of machine learning algorithms, and the question is, of course, concerning your problem, what kind of algorithm you will use. Usually this, of course, is a difficult thing. So you have to think about your machine learning algorithms as kind of models. So what they do is, these models are a simplified version of the observations that you make from reality. So every model is a simplified version of reality. Simplifications in that sense mean that you do discard superfluous details that are unlikely to help in the generalization process of the machine learning model. But to decide about which feature, which observation to discard and to neglect, you have to make assumptions. If you don't do any assumptions about the data, then there would be no reason to prefer one machine learning model above the other. So what you have to do is, you have to make some reasonable assumptions about the data, and of course you have to restrict the evaluation only to a few reasonable models, since trying all of them would be way too complex and would of course be rather costly. So for example, if you have a simple task, first try to evaluate with so-called linear models, which are the most simplest models. And the most simple model, linear regression, we will talk about in this part of the lecture. Okay, what is linear regression? Just imagine here a two-dimensional problem. We have some input x and we expect some output y. And you have some samples, as you see here. What you try to do with the help of linear regression is you try to aim to fit a line into that scattering data that somehow approximates that data. So that given an arbitrary x, you can make a prediction about what y will be expected. And you can do this in the most simplest way, for example, by using an arbitrary linear function, as you see here. So this means you have usually a function which is dependent on one of these parameters. It can also be dependent on many parameters, but these parameters are linear. So there is no x square or something like that. So it's only x, and it can be, of course, different variants of that x. And you try to find exactly that line that fits to the scattering of data. And if you have many parameters, then you are looking for a so-called hyperplane that fits in there. So let's have a look at the mathematics that is behind there. So don't be scared. Linear regression is not as complicated as it might seem. So first of all, what we have is an input vector of real values x, and we have here, let's say, n of them. And we have an output vector, which is also a real number, and we have a set of parameters. We have as many parameters as we have also x's in the input matter, and also we have a constant parameter. This is beta sub 0. And these, of course, also form a vector in a real valued vector space. And then the linear model is quite simple. We say, okay, we try to compute a function f, which is dependent on our input vector x. And this constitutes of the sum of, we have the static parameter beta sub 0, plus, and then you sum up all the products between the parameters beta sub j and the single components of the x vector. And this is the linear model. So what you have to do is somehow you have to estimate the best fitting parameters beta to approximate exactly the data, the scattering of data that you have. So usually then you have a bunch of training data. This is your set D that you have here, and the training data consists of x values and the according y values, and here we have p of those pairs. And then to determine the best fitting function, the best fitting parameters beta, what we do here is we define a cost function or the loss function, which is here the so-called least square cost function. This is L least squares of beta, and this function is rather easily computed. So what you have here, you have you simply subtract your projected output, so the result of the function f, the linear model f applied on the vector x, and you subtract this from the actual output y. And since this value can be positive or negative, what you do is you create the square or compute the square of it and you sum it all up. And what you try to do is you try to minimize this cost function to find the best fitting linear model. So this is the mathematics behind linear regression. Of course, it goes a bit further. So what we're trying to do is here we try to find the line, or in the multivariate case, the hyperplane, that fits best into the given data by minimizing its distance between the data and the line or the hyperplane here. And you do this with the help of the least square cost functions, and this aims at recovering the line or the hyperplane that minimized the total squared length of the error. That's it. So how does it work? How do we really find the optimal beta? So this is a sketch how it works. So first of all, you have to simplify these kind of formulas. What you do first is you extend the vector x, and you also put a 1 into the x. So you extend the x in the position number 0 with a 1. You do this by adapting the length between the vector of the inputs and the vector of all the parameters. Remember, we have this one static parameter, beta sub 0, and for this we need, of course, something in the x vector, and of course this is not variable, so therefore we simply put a static 1 into that vector. So now both of these vectors have the dimension n plus 1, and what we can do here is, of course, we can simply then use these two vectors and create the inner product or dot product of them. Okay, so what we do then is, of course, we take the formula of our linear model and we can write this sum in a rather simplified form by using the dot product between the vector x in its transposed form and the new vector beta. That's it. And with the help of that also we can rewrite the least square cost functions and make it much simpler. And in the end we have something like you see here, a norm between y, which is the output vector, and x and the inner product with beta, and of course all of this has to be squared in the end. And you see here that we put, of course, into that formula the entire vector of all the training data, vector x, and of course this splits up or generates a matrix as you see here. So this is put in there, and of course if you use the notation in that way, you can do all following calculations for optimizing that much more easier. Okay, so we have rewritten now the least square cost function, and what we do now is we try to compute the optimum for our parameters beta by setting the gradient of that function to 0. So this is basic calculus. So what you do is, of course, you take the least square cost function and you set it 0. And of this least square cost function, you first, of course, you do the gradient. And to calculate the gradient of that, you are using the chain rule. Again, basic calculus, look it up in your basic calculus book. And what you see from the function you have here, you have a function which contains a square, and then you have an x inside the bracket. So this is a composed function, therefore you have to use the chain rule. And the result you see here then is -2, and then in parentheses y minus x inner product beta. This is transposed, and then again inner product with the vector or matrix x that you have here. So this has to be 0. So this means the constant factor 2 in front of it does not take into account. So therefore this is equivalent to the second line you see here, and this of course looks much simpler. What we did here is simply we draw the x into the parentheses, and then you come up with x transposed times x times beta minus x transposed times y. And what you do then is you try to think of what is the beta that you have to put in there that this entire formula computes to 0, and this is easily be determined. So the best beta you find here is then the inverse of that inner product x transposed times x times x transposed times y. Okay, you don't have to go deeper into that. This is only to show you that, of course, there is a simple optimization process going on for trying to develop or to learn that kind of line or hyperplane that is used as a linear model for our prediction task. So that's the mathematics behind. Let's try now to use this and to apply it to an example. I have the following example for you, and of course you can look it up in the material for the lecture. We have data collected, not us, so we have copied the data from an interesting data collection website which is called Kaggle, and there is a data set with diamonds. There are samples of diamonds and data of diamonds, which includes, for example, their prices. The price range here is between $300 and $18,000. Then the weight in karat, which is the weight of the diamond. Then we have the cut and the quality of the cut. We have the color of the diamond. We have the clarity, so measurement how clear the diamond is. Then we have its dimensions in 3 dimensions, X, Y, and Z. Then we have a depth and we have a table, which is somehow the widest point of the diamond. So we have this kind of data, and we simply downloaded it and we put it here into a spreadsheet at Google Sheets. You also have here the link to the Google Sheets data where you can directly access and play around with it. And here you see what kind of data we are dealing with. Okay, and what you expect, for example, what we want to do somehow is to predict the price of a diamond. And the easiest assumption is somehow that there might be a relationship between the size or the weight of a diamond and, of course, its price. So let's have a look at that. There might be a correlation between the weight of a diamond and its price. And here we have a diagram where we have on the x-axis the weight in karat and the price in dollars on the y-axis. And you see here, data is prettily scattered somehow, but there might be, of course, some correlation between these two things. Okay, so let's try, and on that data with the math we have just treated or we have just spoken of, let's try to do a linear regression. And what you come up with, if you do linear regression, it will be something like that. And you see clearly, okay, there is a line somehow going through the midst of these scattering of plots, and it somehow underfits the data. It underfits it, which means probably there is not really something like a linear correlation between of them, and probably also other kind of factors somehow play into the game and are an important factor for determining the price of the diamond, which might be, of course, the cut, which might be the color, which might be the clarity. So especially in the area you see here, so for the larger stones, the linear predictor doesn't work anymore. So there, each of the diamonds is, of course, worth less than the predicted value. Okay, so what we need to determine the quality of our prediction is somehow the mean error that a prediction might have that we do here. And for this, of course, there is a formula which is pretty close to our coast function that we have already talked about. And this function is called the root mean square error, RMSE, that we are dealing with. And this is nothing else. So you look over all of your dataset instances that you are dealing with. And what you do here is simply you compare the value of your hypothesis, H, with the value of the expected output, which is Y here. And you take the square of it, you sum it up, M times. Let's say you have overall M instances in your data set, and then of course you divide it by m to normalize it, and then you build the square root over it. And this is the mean or the root mean square error that we are looking at. For our example, what we see here, the root mean square error is about 1,500. Here it's dollars. What does it mean? It means that if we predict the price of a diamond based on its weight, for example, take a diamond of 2 karat, then the prediction would have an error of about $1,500 in the mean or on the average. Of course, this is much more important for the smaller stones than for the larger stones. For the larger stones, if you are here in a price range of 30,000 or 35,000 euro, dollars, then $1,500, it's not such a big deal. But for the smaller one, which are about $1,000 or even less, of course, an arrow of 1,500 would be really heavy. So what we have to do is we have to try to adapt our model in a way that, of course, this arrow becomes smaller. So this arrow is a quality indicator how well your model fits your observation. Okay, what we have to take into account if we look in our data is, of course, for the linear regression task, we would have much more columns here with numbers that we can apply as one of the axes in our linear regression task. What we also have here is we have data that is not expressed in terms of numbers, it's expressed in terms of text strings. For example, here the cut, which could be ideal, premium, good, or something like that, or the color, which is represented by a character, or the clarity, which is also expressed via a code. So what we have to do to include all these into a linear regression model is we have to translate them into numbers. So what you take into account besides the weight might be clarity and color. And since they are non-numeric values, we have to translate them or map them to numerical data. So for example, if you take the colors, we could go for D and say D will be 0, E will be 1, J will be 2, and so on and so on and so on. The only problem that you have to take care of if you translate these non-numerical data into numerical data, that numerical data usually has an inherent dependency. So 1, of course, is closer to 2 than 1 to 5, for example. And of course, this does not necessarily really reflect also the similarity between the non-numeric values that you have used in the mapping. So this is a difficult thing, and what you do there is you have to use another kind of encoding, but this is a more complex task that we will talk about later. Just have a look here at the graphics that we have displayed for you here. Besides the price and the weight we have here on the axis, we have used a few other factors to display. So for example, we have used the color, which determines the size of the blob that you see here. And we have the clarity, which is the color of the blob or of the scatter you see here. And you see here a clear, let's say, somehow relationship that, for example, the red ones are always cheaper or most times cheaper than, let's say, the blue ones or the yellow ones, which are of the same weight. So there is somehow a correlation that has to be considered here. So what we can do for improving our first result first is to include more variables. And the other thing, what we also could think of, maybe there is not a linear dependency. Maybe it's a more complex function. So we can do also what is called polynomial regression. And this is pretty easy. Therefore, I'm telling you here a bit of the math of the linear polynomial regression, which means what we could do is we could simply replace all the inputs of the linear regression to some nonlinear so-called features, phi of x. And then it's the same condition for optimality, so beta doesn't change. But of course, then you are not treating x, but x is a nonlinear feature, phi of x. And features are an arbitrary set of base functions, and each function is linear in beta, and it can be written in the way like phi of x, and you transpose this and build the inner product with beta, and this is denoted as some feature. So based on that, you can simply then, instead of doing linear regression where you're looking for a line, you can look for a curve, which is a polynomial. But you have to keep in mind, for example, since if you are talking about linear features and you have n different features, then you are in the dimension n plus 1. And then if you go by 1 potence higher, so if you go for quadratic features, what you have then is you have to take into account all feature combinations, which in the end gives you a number which is exponential in, of course, the power of exactly your features. And therefore, you see complexity of these polynomials when doing the regression task rises exponentially. So this is a complexity issue you have then. Okay, but putting this on the side, here is an example. If, for example, between our two features, which are the weight and the price, if we try there to do a higher dimensional polynomial regression by the degree of 8, we see that we are already able to reduce the root mean square error from more than 1500 to 1430, which is way better. And you see it here with a curve that we have plotted here in red inside the diagram, that this fits, of course, a bit better compared to the other curve. In the end, if you want to do it perfectly based on linear regression, you have to take into account, of course, all of the features you have. And what you do there is, of course, non-numerical data has to be mapped to numerical data. And also, if you look at your numerical data, sometimes you might have features which have huge numbers, sometimes you might have features which have small numbers. And in linear regression, of course, the size of that numbers influences heavily also the regression task. So what you should do in the beginning is somehow normalize your features. Not that one of the features then gains too much influence, since it's simply the greater number. And of course, you have to somehow encode your non-numerical data in a way that there are no wrong or potentially wrong dependencies. If you're doing that based on the features we have available in that data set, then a multivariate linear regression task on that diamond data gives you an example or gives you a result like that. You can reduce the root mean square error by linear regression to $1,129, which is way up smaller, but of course far from optimal. So this is linear regression, and if you want to further reduce that kind of error, you have to think about other models that you could use to estimate the price of the diamonds. And we will talk about other models in the next part of that lecture.